All right, now that we've had some basic definitions of electrochemistry, what I want to do is show you how these setups actually work for chemical reactions. Okay, and so we're going to try to focus on what kinds of chemical reactions actually take place in these electrochemical systems. So there are different kinds of cells that we have to worry about for these electrochemical cells. One is called a galvanic cell or voltaic cell, and the other is called an electrolytic cell or a battery. And what I'm doing on this figure is showing you the main differences between these two different kinds of systems. Okay, and so on the left here is the electrochemical cell or galvanic cell or voltaic cell. And this one produces electricity as a result of a spontaneous reaction. Okay, and so basically you have one solution with a piece of metal called an electrode. And in this case, this is the anode. And on the other side, you have another solution, another piece of metal, another electrode, which is called the cathode. And the electrons travel from the anode to the cathode. Okay? And this allows electricity to be conducted. The salt bridge in the middle keeps the charges the same. So the salt bridge in this case might be made out of something like zinc sulfate and allows the ions to kind of go back and forth, okay, so that the total positive charge on one side and the total negative charge on the other side is balanced out, okay. So the other example is an electrolytic cell or a battery. That's on the right. This one, we're going to use electricity to actually carry out a non-spontaneous reaction. Okay, and so this might be an example like taking sodium chloride and having it undergo electrolysis to break it apart into sodium and chlorine. So now I still have an anode and I still have a cathode, and the definitions don't change. The anode is still the site of oxidation. So a good way to remember this is anox. And reduction still occurs in the cathode, okay, red cat. So now the sodium ions in the NaCl, because they have a charge of +1, are being reduced to 0. The chloride ions are being oxidized to 0. Okay, and so at the cathode, I have sodium ions gaining electrons to make sodium metal. At the anode, I have chloride ions losing electrons to make chlorine gas. Here's the thing. All of these reactions contain two different electrodes. Okay, there's an anode and there's a cathode. And what I'm measuring is a voltage, a potential difference between the left side and the right side. What I really want to do is know what the potential difference is for just one of these two halves, which is called the half reaction. But because I need both of them to complete the circuit, it's kind of impossible to really do that. Okay, and so what do? Well, we kind of cheat a little bit, and we use a reference electrode, which is called a standard hydrogen electrode. And what happens is we assign the standard hydrogen electrode to have a voltage of exactly 0 volts. So everything else is relative to this number. Hydrogen itself is a gas, and so I can't really have an electrode, piece of metal, made out of hydrogen. And so what I do is I adsorb the hydrogen on the platinum. Okay, so it's kind of on the surface of the metal, and I allow a wire to be kind of transferred to that. Okay, and so this nomenclature here represents the standard hydrogen electrode. Okay, it's a surface of platinum with hydrogen gas on it. And by definition, the voltage for this reaction going from H2 to H plus ions, or in other words, the reduction, going from H plus to gain 2 electrons to make H2, this is exactly 0 volts. Okay. When these numbers are given to you as half reactions, they're almost always given to you as reductions, okay, where they're gaining electrons. So now let me show you something called the Nernst equation, which is actually pretty useful. It takes into account the fact that not everything is under standard conditions. Okay. The standard hydrogen electrode assumes a certain temperature and a certain pressure. and a certain concentration. Okay, so we're going to assume that standard state is a temperature of 25 degrees Celsius, pressures for all the gases are 1 atmosphere, and all the concentrations are 1 molar. But under normal circumstances, I may not have those conditions. I might change the concentration or the temperature. Okay? And so the Nernst equation allows me to take into account these different changes. Now I know that delta G for a reaction at any circumstance is equal to delta G0 for the reaction at standard state plus this extra term called RT ln Q. And so this Q here is something called the reaction quotient. And what I can do is divide both of these sides by minus nu F. Okay, and so nu is the number of electrons that are being transferred, and F is something called Faraday's constant. And so now I have the voltage is equal to minus delta G for the reaction at standard state over nu F minus RT over nu F times natural log of Q. The first term here represents the standard EMF, or electromotive force. So this is minus nu times F times E0. Okay, and so delta G0 for the reaction is just equal to the product of these three things, right? Number of electrons that I have that I transferred, Faraday's constant, and the voltage, or the potential. So that's this equation here. And so if I combine that, I get this equation here. E is equal to E0 minus RT over nu F times natural log of Q. This is the famous Nernst equation. You can use it like it is, but it's actually a bit easier to work a little bit more. If we assume that the temperature is 25 degrees Celsius, RT over F is going to be a constant, right? Because the gas constant is a constant, temperature is a constant, Faraday's constant is a constant. So if we put all these constants together, I get one gigantic constant. And it happens to have units of volts, or in this case, millivolts. It's about 25.7 millivolts. So I could also write this as E is equal to E0 minus 25.7 millivolts over nu times log of Q. Or if you don't like natural log, but instead want a common log, right, log instead of ln for natural log, then we can write it like this. E is equal to E0 minus 0.0591 over nu, number of electrons that I'm transferring, times log of Q. So this equation here allows me to convert between standard state, which is the E0, and non-standard state, which is just the E. Now that you've seen the Nernst equation, let me show you how you can relate this into another equilibrium situation. If you're at equilibrium, the reaction quotient Q is equal to K. And if you're at equilibrium, delta G for the reaction is equal to 0, which means that the voltage is also equal to 0. So if I substitute this into the Nernst equation, I get 0 is equal to E0 minus RT over nu F times natural log of K. Or if I rearrange this a little bit, ln K is equal to nu times F times E0 over RT. This means that I can calculate all these equilibrium constants for all these different reactions just by measuring cell potentials, right, the voltages. This is pretty useful from the practical point of view because a lot of these equilibrium constants can be really, really, really big or really, really, really small, and it might be hard to get directly by looking at things like concentrations. But I can measure them pretty easily by just looking at voltages because I can buy a voltmeter which can pretty easily measure fractions of a volt, which can translate to like super big values for K because of this relationship here. If I have a spontaneous reaction, that means that delta G is negative and the voltage is going to be positive. Okay, these have opposite signs because remember delta G, 0, is equal to minus nu times F times E0. Okay, and so because of that minus sign here, if the delta G is negative, the voltage is going to have to be positive. That means that we can figure out which half reaction is going to occur at the anode and which one is going to occur at the cathode just by looking at what the corresponding standard reduction potentials are for these two things. And remember that because they're written as reduction potentials, one of them is going to have to be flipped, right? The one for the oxidation or the anode is going to have to be flipped. And I flip them in such a way that whichever, when I reverse, when I add the two numbers, I have to get a positive number overall for the voltage, because a positive value for the voltage would be spontaneous, just like a negative value for delta G would be spontaneous. So I'm going to have to flip one so that the overall voltage is positive.